In this video, we're going to discuss the fundamental theorem of calculus, and then we'll kind of briefly introduce some other theorems. So there's two big ideas in calculus, and basically derivatives, integration, and at one point there were two different mathematicians that discovered that they were inverse operations. So when we're taking the derivative, we're really taking the limit of the slope function. When we're integrating, we're taking the limit of the area. And so they're inverses because one's a quotient and one's a product. And we can use that to find the area under the curve. So the fundamental theorem of calculus says if we have an integral with upper and lower bounds, the way we can evaluate this algebraically is to integrate the function first. We plug in the upper limit into that function, we plug in the lower, and we subtract. Okay, so we're going to go through a couple of examples, but when we apply it, notation is very important. So when we integrate a function, we draw this line and we put b to a. This piece has to be here, and then that means that we're going to plug in b first, we're going to plug in a, and then we subtract. There's no reason to put the plus c anymore because it's going to cancel. And to kind of see that is if we integrated and we had a plus c here, then this would be f of b plus c minus f of a plus c, and this c will end up subtracting with the c here, and it cancels out. So no plus c. Again, think of it as this is asking us to find the area under this curve, and area is a number. There's no c in there, so our answer is just a number. And then the total distance traveled, we're not going to practice this a lot, but here's the formula for total distance traveled. Average value, we're going to talk about more in the next video, but it does also use a definite integral, so we're going to have to use the fundamental theorem of calculus. And the second fundamental theorem of calculus, again, we'll go over in the next video, it's kind of a shortcut of when we are taking derivatives of integrals. And again, we'll talk about that in the next video, but it has to do with the fact that they are inverse operations. So for our first example, here this is a definite integral because there are upper and lower bounds, and this just says find the area under this curve from 1 to 2. So if we were to draw a picture, we would get something that is not geometric, so we must use the fundamental theorem of calculus, and that just says let's integrate this guy first. So I'm going to add 1 to my exponent. I'm going to take that original coefficient and I'm going to divide. Then here, since that's a constant, I'm going to give it an x, and I'm going to say that I want to evaluate this from 1 to 2. And then this means we're going to first plug in 2, so I'll get 1/3 times 2 cubed minus 3 times 2. Now I'm going to subtract, and now I'm plugging in the 1. Okay, what's really important here is that we put this in parentheses because this is a binomial. So I'm going to have a 1/3 times 1 cubed minus 3 times 1. And from here, we're just evaluating. So this turns into 8, so this is really 8/3 minus 6 minus 1/3 plus 3. If I combine my fractions first, 8/3 minus 1/3 is 7/3. And -6 plus 3 is -3. You could get common denominators and subtract if you want. The next example, when it's written as a radical, we do need to turn it into a power so that we can apply the power rule. So this is really the integral of 3x to the 1/2 power, and we're integrating from 1 to 4. Again, this says find the area under the curve, so my answer will be a number. So I'm going to add 1 to my exponent first. I'll get x to the 3/2, and then I'm going to divide 3 by 3/2. Remember, we take that second fraction, we flip and multiply. So we're really multiplying by 2/3, which turns into just 2. And I'm evaluating that from 1 to 4. If it's a coefficient, I can leave that in front of the entire fundamental theorem of calculus. I'm going to plug in 4 first, so I'll get 4 to the 3/2 minus 1 to the 3/2 because I plug in the 1. And then to simplify these rational exponents, remember they just turn back into radicals. So this is really radical 4, 3 is the exponent, 2 is the index. So minus the same thing with the 1, and this 2 drops down. And then to evaluate, the 2 drops down. The square root of 4 is 2. 2 to the third is 8. And 1 to any power is this 1. So this becomes 2 times 7, which is 14. Okay? I think the last example we're going to go over today is an example in words. So remember that integration finds the area under the curve. So when it says find the area with this as a boundary, the x-axis, and these vertical lines. If you really want a picture, we could draw a picture here. Okay, so this is a quadratic. It opens upward. You know, it's going to look, I don't know, something like that. It's bounded by that curve, the x-axis, and the vertical lines 1 and 4. So it's going to be this region here. So clearly we actually could, we cannot, because that's a quadratic, I forgot. We cannot use a geometry formula. We must integrate because this is not a geometric shape. So the way we set this up is we say, I want to find the area under this function, which is 3x squared minus 2x. I'm respecting x. I'm going to start here when x equals 1, and I'm going all the way until x equals 4. And now we're just applying the fundamental theorem of calculus. And it's going to give us the area of this kind of trapezoidal looking shape. So when we integrate, again, we're going to add 1 to the exponent. We're going to divide, so we get a coefficient of 1. Here we get x squared. When we divide, we get a coefficient of -1. And I'm going to evaluate that from 1 to 4. So we plug in 4, we'll get 4 cubed minus 4 squared. And I'm going to subtract the entire binomial when I plug in 1. So I'll get 1 cubed minus 1 squared. And clearly 1 minus 1 is 0, so I really have 4 cubed minus 4 squared. 4 cubed is 64, 4 squared is 16, and I'm left with 48. This is the area of that shape. And we're going to save the rest of this chapter for the next video.